And hello, everyone. Welcome to Humanist Canada's monthly webinar series. I'm Anna Popovich, your host this evening. Just to remind you that this webinar will be 60 minutes in length with a Q&A period at the end of the presentation. If you have a question and would like to ask it directly, please raise your hand. At the bottom of the screen, you can also submit your question or comment with the Q&A tool at the bottom of the screen as well. And this webinar will be recorded. Our topic today is Climate Change 2021, the physical sciences basis. And our guest this evening is Dr. Nathan Gillett from the Canadian Centre for Climate Modelling and Analysis. Nathan's research focuses on understanding the causes of past climate change and improving projections of future climate change. Nathan holds a PhD in atmospheric physics from the University of Oxford. He was a postdoc fellow at the University of Victoria, where he worked on the detection and attribution of climate change. In 2008, Nathan joined the Canadian Centre for Climate Modelling and Analysis as a research scientist, where he served as manager from 2014 to 2018. Overseeing the development and application of Canada's Earth System Model. Nathan was also a lead author of the UN Intergovernmental Panel on Climate Change, 4th and 5th assessment reports, and the coordinating lead author of the 6th assessment report, co-leading a chapter titled Human Influence on the Climate System. Nathan, welcome, and it's great to have you, and thanks so much for your time. Over to you.
Thank you. Thanks very much for the introduction. And hello, good evening, good afternoon, everyone. So yes, that's right. I'm going to be talking about the IPCC 6th assessment report. I am just going to try and share my screen. Here we go. Hopefully everyone can see my screen.
Perfect, yes.
Great. Okay, I'll proceed. So yes, that's right. I'm going to be talking about the Intergovernmental Panel on Climate Change latest report. And just for context, the Intergovernmental Panel on Climate Change is a body. It's under the United Nations, under the United Nations Environment Programme and the World Meteorological Organization. I think probably most of you are familiar with it. And so this is the report that came out in 2021, a year and a half ago now, looking at the physical science basis. So the climate change itself, observed changes in the climate system, projected future changes in the climate system. And my next slide here just gives a bit of kind of overall context to this. So the IPCC assessment reports are composed of 3 different reports prepared by 3 different working groups. And as I said already, the one on the left is the one that I was involved in, looking at climate change itself. The second report there in the middle is focused on impacts of climate change, adaptation to climate change, and vulnerability to climate change. And then the one on the right focused on mitigation of climate change, so policies that we can put in place to reduce or limit climate change. And obviously, perhaps the second and third might be a little more closely linked to the sort of interests of Humanist Canada. But that said, the physical understanding of the climate system itself kind of underpins our understanding of impacts of climate change and of mitigation of climate change. So I think we can justify hopefully talking about climate change itself in this talk. So just in terms of what I'll be covering, I'll introduce a little bit about the process that was followed to arrive at this report first. Then I'll summarize some of the kind of high-level key messages from the report. And then I'll go through all the figures, the graphs and so on in the summary for policymakers of the report that will give you a good kind of understanding of the main conclusions of the report. So like I said, I'll start with a bit about the process by which this report was arrived at. And yeah, like I said, these reports are prepared by the IPCC. They come out roughly every 7 years. They're intended, I guess, primarily to inform policymaking, international policymaking on climate change, particularly the COP meetings, for example, like the COP26 that was in Egypt in December, and in the past meetings like the Paris COP that led to the Paris Agreement. So the IPCC is really intended to provide the science that informs policy on climate change, primarily internationally, but also, at a national and local scale as well. And so it's a very thorough and authoritative and comprehensive assessment that we do. The preparation of this report started back in 2018. So, and I was still providing comments on proofs pretty recently. So it's, I would say, more than a 4-year kind of process to arrive at this report. The author team that does this is pretty big. So the number of the lead authors and coordinating lead authors, you can see on the left, there were 234 from 65 countries. And this is intentionally geographically diverse. Authors are, or there's an intention of getting a kind of geographic balance between different regions of the world, between developing and developed countries. And this is obviously great because it gives a diverse range of perspectives into the assessment. One, just as an aside, it does make organizing teleconferences and Zoom calls difficult, as we found out when we went, when things locked down due to COVID-19 and we couldn't meet in person. It is a little hard to find a convenient teleconference time. But okay, so, but yeah, it's intentionally diverse, and that's certainly a strength of the process. The next line here gives the proportion of women to men. Obviously, and perhaps not surprisingly, there are certainly more men than women working in the field, but the intention is to work towards getting more equity there. And you can see there's some more distance to go there, but certainly around 30% of women authors. And then there was a mixture of people that were new to the IPCC and that had participated in previous IPCC assessments. I've been in this community for quite a while now, so I've certainly have participated in previous assessments before. But now looking at the evidence base that this report was based on, well, you can see here, more than 14,000 scientific publications were assessed. And the report, as authors of the report, we don't do new research that goes into the report. It's an assessment report, which means it's looking at the results published in peer-reviewed scientific literature and basically distilling conclusions from that. And as you can see, it's a lot of publications. There is a lot of science published on climate change, and our main focus is on the reports, the studies that came out in the last 7 years since the last assessment report. The reports also go through a lot of reviews. I think there's 4 rounds of reviews on the chapters. And as you can see there, over 78,000 review comments were considered and responded to as part of the process. So a lot of those are from scientists and from experts, but also government representatives are involved in providing comments on the later drafts of the chapters and on the summary for policymakers. And the intention there is to guide the process, make sure that the results are kind of fully relevant to informing climate policy. Okay, and at the bottom here, you can see that 46 countries commented on the final draft there. So there was obviously not every country, but a lot of countries providing comments and input into the review of the final draft. Okay, so that's a little bit about the process. Like I said, very comprehensive, very thorough in terms of the literature assessed. Okay, so now I'm just going to go through some of the key messages coming from the report. These aren't actually in the report, but they were kind of distilled from the report at the end of the process. Recent changes in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. And I'll show you some of the evidence for that in one of the later slides. It's indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and droughts, more frequent and more severe. Yeah, this was actually, we made the assessment that it was unequivocal that humans were warming the climate system. This is a stronger assessment than previous reports have made. Climate change is already affecting every region on Earth in multiple ways. You know, at the start 20, 30 years ago, we could see climate change in terms of the global average temperature. Now it's, you know, very clearly emerging, not just in the global average, but in every region in Earth in a lot of different ways. And the changes we experience will increase with further warming. Unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees Celsius will be beyond reach. That is, yeah, a clear conclusion of this assessment. You know, for the decade assessed in this report, we'd already observed a 1.1 degree of human-induced warming. By now, it's probably about 1.2 degrees. So it is really a very rapidly closing window if we want to limit warming to 1.5 degrees. There's no going back from some changes in the climate system. And indeed, the warming itself and most climate change is not reversible on human timescales without actually, unless we remove carbon dioxide from the climate system. But certainly some changes can be slowed. In fact, I think, you know, if we're successful in reducing emissions, getting to net zero, I think, you know, all climate change can be slowed. And others can be stopped by limiting warming. You know, we can, if we get to net zero, we can stop further global warming, and there's other aspects of climate change that we can limit in a similar way. But to limit global warming, strong, rapid, and sustained reductions in carbon dioxide, methane, and other greenhouse gases are necessary. And you know, another conclusion of the report, which isn't stated here, but if we want to stabilize global warming, then we have to get to net zero carbon dioxide emissions. And this would not only reduce the consequences of climate change, but would also improve air quality. So if we think of, well, for example, if we burn coal, we emit greenhouse gases, but we also emit pollutants like sulfur dioxide that damage air quality. These have serious impacts on human health. So by mitigating climate change, we can also improve air quality, which has other benefits for human health. Okay, so I've covered all those kind of distilled high-level conclusions. For the rest of the talk, I will go through the figures in the summary for policymakers. These are the kind of high-level findings of the report, and I'll describe them in a bit more detail. And of course, there should be plenty of time for questions afterwards. So if you have questions, feel free to ask me about them in more detail afterwards. So this is the first figure. This shows that human influence has warmed the climate at a rate that is unprecedented in at least the last 2,000 years. What this figure shows, so on the left, we're looking at the last 2,000 years. The gray here is reconstructed temperatures over that period. This is from things like tree rings and other so-called paleoclimate data. And then the black on the right is, since 1850, is a direct estimate of the global average temperature from thermometer measurements. You can see that the steep rise in temperature since 1850 is, well, you can see immediately on this graph that it's unprecedented in the last 2,000 years. Certainly there are some variations in climate prior to human influence. These are caused by things like variations in the sun's brightness, by large volcanoes, but nothing like what we've seen in the last 150 years in the period in which greenhouse gases have increased strongly. Looking even further back, the graph does also show well, as it's labeled here, the warmest multi-century period in more than 100,000 years. So this is something like 5,000 or 6,000 years back in the mid-Holocene. You can see that we're now emerging into temperatures that are kind of above this estimate for the warmest multi-century period in the more than 100,000 years. So we're now emerging into a climate that the Earth hasn't seen for more than 100,000 years. Okay, on the right, we can see the period since 1850 in more detail. The black, again, shows the observed global average temperature over this period. But this is now compared with climate model simulations, which include both human and natural influences. Maybe I'll just briefly introduce what climate models are. So these are computer models of the climate system based on our knowledge of the physics of the climate system. They're in fact similar to weather prediction models, but they're run over a longer period, and they include more processes that are important for climate change. So Brown is climate models, not just one model, but a selection of models from around the world, including the Canadian Earth System model. So Brown is with human influence, and then this green-blue color is with natural influences only, and those are solar variations and large volcanoes. So you can see that on average, the models reproduce the observed warming well when they include human influence, but the models do not capture the observed warming based on natural influences only. So it's very clear evidence that human influence has warmed the climate system. Sorry, my slide is frozen. Let me see if I can get to the next slide. There, good. Sorry, skipped too far ahead. Okay, so let's unpack. So far I just talked about human influence in general. This slide unpacks the different components of human influence on the climate, on the global average temperature. So as it says there, observed warming is driven by emissions from human activities, with greenhouse gas warming partly masked by aerosol cooling. So I'll take you through this figure from left to right. On the left is an estimate of observed warming for this period 2010 to 2019, so a recent decade, compared to 1850 to 1900, and it's about 1.1 degrees in terms of global warming. Like I said, if we went right up to 2022, 2023, this would be a bit higher. Okay, and then the center panel shows the contributions to that warming. So the left there is the estimate of the total human influence on the warming. It's almost exactly the same as the observed warming, about 1.1 degrees. But that human-induced warming is driven by an even stronger greenhouse gas-induced warming, which the estimate here goes from 1 to 2 degrees. So these are greenhouse gases like carbon dioxide, like methane. But this warming has been offset by cooling due to aerosols. This is things like, well, for example, when we burn coal, release sulfur dioxide, that gets turned into sulfate in the atmosphere, and that's reflective, and it reflects some of the sunlight back to space. That acts as a cooling influence on the climate. So yeah, some of the greenhouse gas warming has been masked by aerosol cooling. The figure on the right goes into this in even more detail. This is looking at the response to emissions of these different gases. You can see that carbon dioxide is the biggest contributor to the warming, but the emissions of methane also making a pretty strong contribution to the warming. I won't go through all of these different components, but you can see that the strongest cooling component is sulfur dioxide. As I mentioned, one of the big sources of sulfur dioxide is coal burning, and that is a cooling influence on the climate. I mean, you might think, I guess, from a climate perspective, that is in a way a good thing, but the health impacts of sulfur dioxide and the ecosystem impacts it causes acid rain, for example, are pretty serious. So we want to reduce sulfur dioxide emissions, and that means, unfortunately, that will kind of unmask some of that greenhouse gas induced warming. Okay, so that was past contributions to past warming. How do we expect emissions to change in the future? And this is a graph showing the different so-called scenarios of emissions of greenhouse gas in the future considered in this assessment report. So on the left, this is carbon dioxide emissions going from 2015 through to 2100. You can see that there were 5 different scenarios considered in the report. They vary pretty strongly in terms of how they are projecting emissions to evolve. And the different scenarios, there's different kind of socioeconomic assumptions underpinning them, evolution of the world's population, evolution of technology, and also whether or not there are policies brought in to mitigate climate change. These 2 highest kind of red emission scenarios have strongly increasing greenhouse gas emissions. And one more thing to say is these scenarios were actually kind of developed probably around 10 years ago, so quite some time ago now. I think, I was mentioning to Anna before the talk that I'm kind of by nature an optimist, and I think one thing that has a positive thing that has happened in the last 10 years is that we can now say that these higher emission scenarios, and I should say this isn't a conclusion of the report, but this is, I think, what I'm just saying now, these higher emission scenarios are looking a lot less likely now, which is a good thing because we've got some policies to limit emissions in place, and countries, the Paris Agreement has come out since these were developed, and yeah, so I think these higher emission scenarios are less likely. The orange scenario here is probably the closest one to the kind of current policies, although maybe the policies wouldn't show such a strong decrease. These blue scenarios are ones that would get us close to meeting the Paris targets. The dark blue would have us probably limiting warming to 2 degrees. The lighter blue one would have us with a chance of limiting warming to 1.5 degrees. One thing that you can notice about these blue scenarios is that the emissions actually go below 0 in the latter half of the century. And that means actual removal of carbon dioxide from the atmosphere. So that means either technologies to take carbon dioxide out of the atmosphere and store it, things like or planting trees is another one, although that's limited in scope. But yeah, just to note, these have negative emissions, so-called negative emissions by the end of the century. Okay, over here you can see changes in these other greenhouse gas emissions, as well as changes in sulfur dioxide, which I already mentioned, which is an important pollutant, but which is projected to decline under most of these scenarios. Okay, so how does the climate respond to these scenarios? What are the projected temperature changes that we would expect in response to these scenarios? Well, as I said, the future emissions differ very strongly between these different scenarios. So the range of temperature projections differs a lot. So on the left, in each case, the left bar is showing the total projected temperature change by the end of the century, excuse me, relative to 1850 to 1900. And it's composed of the darker part is what we've observed to date, about 1.1. And then you can see that, for example, in this lowest scenario, which has very aggressive emissions reductions, the temperature is, just, I think the best estimate is 1.4 degrees, so below 1.5. But like I said, that has extremely ambitious and dramatic emissions reductions. Like I said, the orangey color there is probably the closest to current policies. That has, well, it's about 2.7, 2.8 degrees of warming, global warming by the end of the century. So that's already you know, more than twice as much warming as we've observed, and more than twice the impacts would be expected to be, you know, at least twice as big as well. So that's still a very significant warming with very big impacts. You can see these higher emission scenarios, as you would expect, have even higher, you know, which, you know, would be very, very profound changes in climate. Okay, yeah, I think I'll keep going. Okay, so far I've talked about changes in global average temperature, but what does the regional pattern of temperature change look like? So with every increment of global warming, changes get larger in regional mean temperature and in precipitation. So precipitation is rain and the kind of rain and snow summed together, and soil moisture. And that's what I'll show you in these slides. So the top row here is showing the observed change per 1 degree Celsius of global warming. You can see that in general, the land warms more than the ocean. You can see that the Arctic in particular is warming more than the lower latitudes. So this figure here is the observed change. This one over here is the simulated change from climate models. You can see that they agree generally pretty well. The observed change shows warming almost everywhere, with the exception of this small region in the North Atlantic. Might be due to different changes in ocean circulation. In terms of what we can expect in the future, the pattern of warming basically intensifies. It scales with the global mean warming. So by 1.5 degrees warming, you can see, you know, as you would expect, stronger warming, particularly over land, particularly over the Arctic. This is already, you know, quite big, up to, you know, 5 degrees or so. Yeah, one thing just to mention here is, you know, Canada, obviously being land and also being a high latitude country, is expected to, or is observed to be warming at a higher rate than the global average, and is also expected to continue to warm at a higher rate than the global average, roughly twice the global average rate. And you can see that at these, you know, much higher warming levels, like 4 degrees, the local temperature changes are getting extremely large. Okay, so that's temperature. What about changes in rainfall or in precipitation? You can see that, so whereas with temperature, it's projected to get warmer everywhere, with rainfall, it's projected to get wetter in some regions and drier in others. You know, one way, a sort of simplifying way of saying this is that the wet regions get wetter and the dry regions get drier. It's a bit of an oversimplification, but yeah, generally we can see moistening, more rainfall in the Arctic and the Antarctic, more rainfall in parts of the tropics, particularly the equatorial Pacific, but then more rainfall in the mid-latitudes as well, but then drying in some regions like the Mediterranean, like, for example, Mexico and parts of the southern US. And again, those changes just intensify with the higher levels of global warming. Okay. Okay, this next figure is looking at changes in extremes. So far I've talked about changes in average climate, but extremes are really important for climate impacts. Often it's not just a change in the average conditions that has the biggest effects on people, but changes in the occurrence of climate extremes. So projected changes in extremes are larger in frequency and intensity with every additional increment of global warming. So, you know, similarly to the mean changes, these changes will intensify the larger the global warming gets. So the first part of the figure here is looking at changes in hot extremes or heat waves over land. On the left, this is looking at, so this is for a 10-year event. So an event that would happen like once in every 10 years in the pre-industrial climate in the 19th century, say, is now likely to occur about 3 times every 10 years. So it's already, much more likely to occur, so about 3 times more likely to occur. This is an average over the globe. And then if we look at these higher warming levels, of course, these heat waves become more and more common, such that what was a 1 in 10 year event in the pre-industrial climate by global warming of 4 degrees happens almost every year. And this is kind of at the local level. Okay, the right here shows basically a similar thing for a 1 in 50 year event, except the relative change is even larger for a rarer event. Okay, so what about changes in heavy rainfall? Okay, actually, sorry, one more thing I'll say about the hot temperature extremes over land. Some of you might remember the heat wave that we had in Western Canada in 2021, in BC in particular. This is an example of a heat wave that was whose odds were very much increased by human-induced climate change. So I was involved in a study on that heat wave. Yeah, you might remember it killed more than 600 people, so it was a very deadly event. And the study concluded that that heat wave would have been almost impossible without human-induced climate change. Looking at heavy precipitation, so extreme rainfall, we see a similar thing. Climate change is intensifying extreme rainfall. A warmer atmosphere can hold more water vapor, so it can a warmer atmosphere will have more intense rainfall, extreme rainfall. If we look at the figure, so a 1 in 10 year event in the pre-industrial climate now occurs about 1.3 times as often, so like a 30% increase in probability. Looking at these higher warming levels, for example, at a 2-degree warming level, there's about a 70% increase in probability of that kind of event. So we see also increases in the frequency of occurrence of heavy precipitation events. And then lastly, the last thing that's shown in this diagram is changes in droughts, agricultural and ecological droughts. And this is specific to drying regions, so those regions where the rainfall is projected to decrease. So in these regions that are drying, droughts are becoming it's not just a general decrease in rainfall, the droughts are becoming more frequent, as you would expect. So a 1 in 10 year event in the pre-industrial climate is now 70% more likely at 1 degree warming, and then becomes increasingly more likely at higher levels of warming. So this figure is just showing that extremes in climate, be it heat waves, extreme rainfall, and drought in drying regions are all projected to increase in intensity with increasing global warming. Okay, so this figure is now looking at how climate will evolve, how a number of key climate variables will evolve. As it says there, human activities affect all the major climate system components, with some responding over decades and others over centuries. This figure shows global average surface temperature relative to 1850 to 1900. The black is simulated past changes. Again, I already showed you that was similar to what has been observed. If we look into the future, as I mentioned before, these the two blue scenarios, SSP 1.9 and 2.6, are the only ones that have a good chance of keeping the climate below 2 degrees. So they're consistent with the Paris Agreement target of limiting warming to well below 2 degrees. You can see that the light blue one, which again has extremely rapid and very rapid reductions in emissions, just about manages to keep the global warming below 1.5 degrees. The SSP2 4.5, that's roughly in line with kind of currently implemented climate policies, but sees about, well, I think that in that scenario, it's about 2.7, 2.8 degrees. Yeah, that's in line with what the UNEP emissions gap report, so a report that came out this year or last year, concluded that current policies would get us to about 2.8 degrees of warming. You can see these other higher emission scenarios give us much higher warming levels by the end of the century. Okay, what about Arctic sea ice? You know, Arctic sea ice is a kind of a key climate variable that people are aware of. You know, it's already been very substantially affected by climate change. How is it projected to change in the future? So the black is simulated past change, and it shows a big decrease, which we've observed a big decrease in especially summer Arctic sea ice area. And that's projected to increase in the ice area is projected to decrease in the future under all the scenarios. You know, even the scenarios with rapidly decreasing emissions show for the next couple of decades, because there's some inertia, they show continued decreases in September Arctic sea ice area. But so this dashed line here is 1 million square kilometers. It's a threshold that's usually used to define a kind of practically ice-free Arctic. You can see that the only two scenarios that avoid an ice-free Arctic are these two blue scenarios here, which managed to stabilize the ice area by about the mid-century. But under all the other scenarios, including this SSP2 4.5, which is roughly similar to climate policy, current climate policies, we could expect an ice-free Arctic in summer by the end of the century. And then lastly, the last variable shown in this figure is ocean surface pH. So this is a measure of ocean acidity. Ocean acidification is, well, is already having big impacts on marine organisms. It's driven not directly by climate change, it's driven directly by the amount of carbon dioxide in the atmosphere. And the carbon dioxide dissolves in the ocean and it makes it more acidic. So we can see that there is already an acidification of the surface water that's been simulated. And that similarly is projected to continue for the next few decades. You can see that because the surface ocean pH responds pretty much directly to the amount of carbon dioxide in the atmosphere, in these scenarios with rapidly declining and then negative emissions, the pH decline kind of stabilizes or even starts to recover. But again, like just to emphasize, that's associated with actually removing carbon dioxide from the atmosphere. And then in these other scenarios, the decline continues, although it's, of course, limited in the current policies compared to these higher emission scenarios. It is relatively limited. Just for some context, another IPCC report, the special report on 1.5, assessed that even at 1.5 degrees warming, 50 to 70% of coral reefs would be destroyed, and at 2 degrees, more than 99%. So that's I think that's a pretty kind of shocking statistic. And that's driven partly by ocean acidification, partly by ocean warming. Okay, sorry, yeah, there was one more variable in this figure. It's global mean sea level change. We've already observed global mean sea level increase about 20 centimeters. And that is projected to accelerate into the future, whichever scenario we follow. The sea level responds very slowly to emissions. So there's two things that are driving it. One is the ocean absorbing heat from the atmosphere, which is a slow process. And the other is melting, well, two main things. The other is melting of glaciers, and particularly ice sheets, the Greenland ice sheet, the Antarctic ice sheet. And those respond very slowly to changes in the climate. So yeah, that's something that kind of is projected to continue for a long time. And I'll show that again actually on the next slide. Overall, you can see the ranges from about 0.5 meter to 1 meter for these likely projections. One thing that was kind of new in this assessment, it was consideration of this so-called kind of low likelihood, high impact future. So there's basically uncertainties in ice sheets, instabilities, particularly in the Antarctic, in the West Antarctic ice sheet, which mean that we can't rule out even much higher rates of sea level rise than are assessed here, even though they're less likely. But under this high emission scenario, this much higher rate of sea level rise is possible. And as I mentioned, sea level is a very slowly responding component of the climate system, if we look out to 2300, the sea level has continued to rise a lot, even under this low emission scenario, SSP 1-2.6, with these reductions in emissions, negative emissions. We're still seeing about 0.5 to 3 meters of sea level rise by 2300. And I mean, that is, quite a long way in the future. On the other hand, if we compare it to how long cities have been where they are by coasts, we can think that it is going to lead to major disruptions on that longer time frame. And then for the high emission scenario, the sea level rises are even much larger, and these under these low likelihood but still possible futures, this even sea level rise greater than 15 meters cannot be ruled out. Okay, let's move to the next one. Okay, so this is the final figure in the summary for policymakers. This is showing the relationship between the warming of the global average temperature and the cumulative amount of carbon dioxide emitted into the atmosphere. And this is something that has been kind of realized since, well, actually in the last assessment report as well, and it's actually based quite a bit on Canadian research. What this figure demonstrates is that the warming is proportional to the cumulative amount of carbon dioxide emitted into the atmosphere. It doesn't really matter how you emit that carbon dioxide, if you put it all into the atmosphere at once, or if you gradually emit it over a long time, the amount of warming that you get is almost the same. But anyway, what you can see here, this is showing the relationship between the warming and the cumulative emissions. One kind of consequence of this kind of relationship is that if we want to limit the warming to a particular level, say 1.5 degrees, we can kind of read off this graph a level of cumulative emissions that we should not exceed if we want to avoid warming more than that level. And well, the blue line here is it's corresponding to this low emission scenario. It's approximately consistent with 1.5 degrees. You can see it has about 500 gigatons of CO2 remaining, and that's actually only about 10 years of emissions at the current rate. So again, that's just emphasizing that limiting warming to 1.5 degrees is a real challenge. Okay, I think I will move to my final slide here. Just to say, this just has links to the IPCC website where you can find the reports, an interactive atlas where you can look at local projections of climate change for your region. And I've also added a couple of links to Canadian climate change resources, one to the Canada in a Changing Climate report, including the Canada's Changing Climate report, which is the one that's focused on climate change itself, as well as the Climate Atlas of Canada, which again is will allow you to look at kind of projections for your particular region. So I think I will close that and open up for questions. Thank you.
Great, thank you, Nathan. Can you see me?
Shall I stop share?
Yes, please.
Okay.
Yes. Okay, so let's go to our questions. The first question, where did the 1.5 degree limit come from? And I think you addressed that in your charts, but maybe I can add to that or change the question. So this is one of the possible scenarios, right? So in your opinion, is there a scientific consensus or a majority opinion as to which scenario is most feasible, most likely? And here's a quote from the Group 3 report: without a strengthening of policies beyond those that are implemented by the end of 2020, current policies, there could be a global warming of 3.2 Celsius by 2100. Medium confidence.
Thank you. Yeah, okay, I'll try and address those. So I can try and speak a little bit to where the 1.5 degree limit came from. I think, well, I mean, there's a lot of work on impacts of climate change. These were assessed, and there was there's assessment that, I mean, the impacts of climate change increase the more the warming, the larger the warming. But I think there was some work that was, arguing that beyond 2 degrees, the impacts become, very much more marked. I think it's basically, I think it also came from negotiations kind of under the COP process. And basically, this, I think, I'm not certain of this, it's a little bit outside my domain, but the small island states in particular argued that even 2 degrees of warming, and we can see that in the sea level rise plots, would have huge kind of existential threats to some of those countries, and that we need to act to limit warming to less than 2 degrees to 1.5 degrees. So I think that was a kind of a conversation that was happening 10 years ago prior to the Paris Agreement. So I think that's probably where it came from. The IPCC special report on 1.5 degrees did demonstrate that a lot of impacts are substantially worse at 2 degrees than 1.5 degrees. So if we really should limit climate warming to 1.5 degrees if we can. And then on your second part of the question on the feasibility of the different scenarios, sort of what has typically been the kind of practice for climate scientists like me is to just say, well, we just get given the scenarios, we can tell you under this scenario, this is how the climate's going to change. But that, I think that's less useful for people that actually want to, plan for climate change and adapt. So, yeah, I think as I mentioned in the talk, and as you just quoted that result from the IPCC Working Group 3 report, I think something like current policies give something like a 3 degree warming by the end of the century, best estimate. Yeah, it's a little bit higher in the IPCC assessment, which came out a couple of years ago than the UNEP emissions gap report that I think was quoting 2.8 degrees most recently. So somewhere around 3 degrees from current policies. I mean, it's not my area, but I think I hope that we're going to add more make climate policy stronger going forward, not kind of backslide and go back. I mean, one positive is that renewable energy is getting cheaper, which is and it's often cost competitive with fossil fuels, so that would support us going towards lower emissions. But yeah, so I think, I mean, hopefully that is an upper limit on future emissions. Current policies are an upper limit on future emissions. And in terms of whether the lowest emission scenarios are plausible, personally, I think probably not. But I would hope so. I would hope we can reduce emissions rapidly and hopefully get to net zero. Thanks.
Thank you. Next question. Why do politicians continue to stress the need for population and economic growth forever when it seems obvious that this approach is not sustainable and allows poor decisions to be made repeatedly?
Yeah, I mean, that's a good question. Yeah, I mean, that is definitely a bit outside my area of expertise. I mean, there are, like I said, that is outside my area of expertise. I believe that the scenarios with reductions in emissions do probably still have some economic growth in them, but certainly, the scenarios with less population growth will tend to have lower emissions, and that will tend to make it easier to limit emissions and to limit climate warming. Yeah, I mean, I'm not sure I can. It is, like I said, outside my area of expertise. But obviously, there are politicians are concerned about their voters and about there are some advantages of economic growth in terms of promoting well-being. There could be, but yeah, like I say, I don't think I'm going to comment more on that. It's outside my area of expertise.
Okay, next question. I noticed global surface temperature dropped quite dramatically in the 90s and rose again around 1993. Was this due to changes in politics at that time, such as Russian breakup? Not sure if you're referring to the breakup of the Soviet Union, but.
Thanks. Yeah, good question. I was planning to point that out in my talk, but I didn't. Actually, no, it's the Mount Pinatubo eruption, which occurred in 1991. That put a lot of volcanic ash in the stratosphere, and that cooled the climate for a couple of years. That's something that we can simulate in climate models, and we see it in observations. And yeah, Pinatubo was the last big volcanic eruption that really altered the climate. There are other ones, if we look further back in history, Agung in the 60s, Krakatoa in the 1880s. And yeah, they do have an influence on climate. It lasts, well, it's strongest in the first couple of years after the eruption, but it tails off, 5 years after, by 5 years after the eruption. Thanks.
Thank you. Can you give us a summary of the measures and policy required for the lowest carbon emission scenario?
Yeah, so well, I in terms of the emissions, certainly, yeah, that reaches net zero carbon dioxide emissions, I believe around in the 2050s. So that means by the 2050s, any kind of remaining carbon dioxide emissions are compensated for by removal of carbon dioxide from the atmosphere, not in natural sinks, but by human removal of carbon dioxide from the atmosphere. And then, yeah, so that's not that long. I mean, the 2050s is 30 years from now. So yeah, it needs, well, I mean, again, not exactly my area of expertise, but it means, electrifying everything and then getting the generation of electricity to be carbon free, as well as, industry and things like concrete and steel. You have to decarbonize those sectors as well. So yeah, I mean, I don't, it's not impossible because there are scenarios that will get there, but it's pretty difficult to get there that quickly.
Thank you. Next question. I noticed one glaring exception on your map. So the wet areas get wetter and dry areas get drier pattern. The Sahara Desert was showing getting wetter. What is it about the Sahara that would buck the trend that you described?
That's an interesting question. Actually, I can't, I don't think I can give a good answer to that. I did notice that when I was preparing the talk. I would say that the idea that the wet regions get wetter and the dry regions get dry is kind of an oversimplification. I think that probably, like I say, I can't give a very good answer. I think it's probably associated with like a northward shift in the regions of heavy rainfall in that area. But yeah, I'm sorry, I should be able to, but I can't give a really good explanation for that.
Okay. Next question is the current population is 8 billion with the projected growth up to 10 billion. What is the likely % change in temperature related to this increase?
Well, I mean, it depends how you kind of divide up the emissions. I guess the one, you can look at it in terms of changes in per capita emissions, and then obviously if you get a 25% increase in if you keep the same per capita emissions, you increase the population by 25%, then you increase the emissions by 25%. But hopefully at the same, we're not just going to keep per capita emissions hopefully at the same level. Hopefully we're going to reduce them, but certainly an increase in global population makes it harder to meet emissions targets.
Thank you. Here's a question that actually came by email from a member. In order to remain well-informed as ordinary citizens about the climate change status and remedial action, what sources, journals, blogs, authors can you recommend?
Yeah, okay, good question. I saw that question before the talk, and that did prompt me to add a little bit more on resources to the final slide. So, I mean, it is maybe a bit technical, but the IPCC reports themselves are authoritative sources. The summary for policymakers are, well, they're not that long, although they are still quite technical. You can also read the press releases that were released with the reports, and there's also frequently asked questions that are intended to be for a general audience that kind of address issues on climate change. Like I said, for Canada, the equivalent is the Canada's Changing Climate reports, which kind of summarize things for Canada. Yeah, I mean, I found that just in general, the quality of reporting on climate change, I would say, is generally better these days than it was like 10 or 15 or 20 years ago, when there was always this kind of false idea that they had to pit a climate skeptic against every piece of kind of climate news. So, you know, I think a lot of news outlets are doing better in terms of their coverage of climate change. But yeah, I think I'll leave it at that. Thanks.
Okay, now I do have to ask this question, and it's a bit long, so please bear with me. Do climate skeptics have a point? According to Columbia University, and you know, this is a stark figure, the current warming is occurring 10 times faster than it did in the past when Earth emerged from the ice ages, at a rate unprecedented in the last 1,300 years. So this is clearly attributed to human activity, not natural causes. However, if we take a long view of history and look at climate cycles going back tens of thousands of years, not 1,000 years, right? And the ascending global warming curve. So hypothetically, where would we be, the planet, if we factor out the impact of humans, of the human plague, say, since the Industrial Revolution, right? So how significant is the human contribution in light of millennial climate oscillations, even if we do agree that it is alarming?
Sure. Good question. So, I mean, I think that question is partly addressed by the first graph that I showed, which showed that, okay, so it was showing the period just the last 2,000 years, but certainly as you saw on that graph, the trend that we've seen in the last 150 years is much stronger than anything we've seen in the last 2,000 years. The same would be true if we extend that for the last 10,000 years. And I did show you that the warmest period in the last 10,000 years. If we went even further back, we would see the warming at the end of the last ice age, which is, the absolute warming is bigger than, you know, the warming that we've observed due to human influence, but it occurred much more slowly over a longer period. To get to your specific question on where would we be without human influence, well, that was shown by those simulations with just natural climate influences only, and so the climate would be about 1.2 degrees global average cooler than it is today. The speed of that human influence is a lot faster than kind of geological timescale climate changes, or the climate change associated with orbital variations. It would be basically a similar climate to what we saw in, say, 1850. Is where we would still be today. On an even longer time scale, we would be going into an ice age in thousands of years. But in terms of where we would be today, similar to the climate of 1850.
Thank you. Always curious about that. Okay, are there any estimates on how climate change is going to affect the birth rates in the future? So I'm not really an expert on that. I don't think I can really give a good answer to that. Certainly, as the Working Group 2 assessment report of the IPCC has showed, climate change is already having big impacts on people and will potentially have much bigger impacts in the future. With changes in agriculture, even changes in heat stress, a lot of these kind of changes. Excuse me, how this will filter through to
birth rates, yeah, there may be research on that, but I'm afraid I'm not aware of it. Yeah, I can imagine it will have an effect, but I don't think I can give a good answer.
Thank you. Okay, so we do have a couple more questions, if that's okay with you, Nathan. Any thoughts on how to counter the increasing disinformation? How can scientists improve messaging around this issue?
Yeah, that's a good question. Yeah, I don't know if I have any really good answers to that. I mean, I think being proactive in messaging, yeah, be kind of responding rapidly, you know, to media and so on. Yeah, it is true that there is. Yeah, it's a challenge, I think, but yeah, those are a couple of ideas. I'm not a big expert in that field, but yeah.
Okay. Does CO2 break down? If yes, how long does it take?
Good question. So in terms of the carbon dioxide in the atmosphere, it is taken up by various processes. So the immediate ones are take up of carbon dioxide by the land, by plants and soils and so on. And then also it gets dissolved into the ocean. It gets taken up by organisms in the ocean. So some fraction of carbon dioxide is taken up quite rapidly by those sinks, but another fraction, it takes a really long time to be taken up from the atmosphere. There are processes in the ocean that can remove it on kind of more multi-millennial timescales, but yeah, so it is gradually removed from the atmosphere, but it takes a really long time. And in terms of the temperature response, that's kind of delayed behind the carbon dioxide response. The temperature, even if we stop emitting carbon dioxide into the atmosphere today, the temperature will stay, you know, roughly constant for thousands of years, perhaps probably tens of thousands of years. So to get back to the climate that we would have had without it, yeah, tens of thousands of years.
Okay. Does the lowest emission scenario specify a required date or time period for an end to fossil fuel extraction?
Well, I mean, in the scenario, you can see when emissions reach net zero. And like I said already, for carbon dioxide, it's about in the 2050s. That is, so that's achieved by, yeah, pretty much reducing fossil fuel extraction to close to zero. One technology that is in some of the scenarios is some fossil fuel burning with carbon capture and storage. But yeah, to get to net zero, you pretty much have to stop burning fossil fuels and releasing the carbon dioxide into the atmosphere. Yeah.
Do any of the standard climate change simulations show that the Atlantic conveyor belt will fail?
So generally they show a weakening of the so-called meridional overturning circulation, but generally not a sudden collapse, although the assessment is that can't be completely ruled out.
Are you familiar with the Energy Transition Show podcast with Chris Nelder? And if so, would you recommend it?
Sorry, no, I'm not familiar with that.
Okay, thank you. And again, I must ask the following question. Is there a scientific forecast or conversation in the scientific community about the consequences of the ongoing war in Ukraine, specifically the energy war?
Thanks. Yeah, so I saw your question. I did look in the UNEP emissions gap report, which came out a few months ago. And so basically the consensus is that, well, no, there's not a clear kind of conclusion as to the net effect of it on greenhouse gas emissions. There are some potential positives in terms of obviously reduced burning of gas in Europe, for example, in terms of the understanding that renewables are less kind of susceptible to geopolitical tensions than fossil fuels. On the other hand, there has been more investment in some fossil fuel infrastructure like LNG. So there's factors that act in both directions and no clear consensus on the kind of net effect.
And finally, do you support nuclear energy as an alternative source? What's your take on this whole debate?
Yeah, okay, good question. I would say that, I mean, there's pluses and minuses I can certainly see. I think that just personally, I don't have a strong view one way or the other. I mean, on the plus side, yeah, it's low, close to zero carbon technology. On the negative side, I think renewables are getting cost competitive, or probably are already cheaper than nuclear. So I would not think that like expanding nuclear in a big way is probably the best way to go. But at the same time, we probably don't want to shut it down immediately because it is a low carbon technology. But yeah, that's just my view. I think I'll leave it at that. Okay,
well, thank you so much for your wonderful presentation, very informative, and thanks to the audience for attending the webinar. Just a couple of final comments. If you have a moment to share your thoughts about the webinar or suggest a topic or speaker, please fill out the survey. You will find the link in Zoom's follow-up email. And do join us for our next webinar in a month on Sunday, February 26th at 3 p.m. Eastern on the mythology of psychology with Professor Rami Gabriel from Columbia College, Chicago. And as always, you can find more information about our upcoming webinars and events on our website, social media platforms, and newsletter. Thank you all, and thanks again, Nathan. Thanks for your time.